Another interesting problem that we could have a look at from our exercise booklet is once again this task number 19 about the maximum power transfer theorem. I'm quite sure that there's also a nice worked out solution and example from the last semester, but we can maybe try to do another quick simulation in LTspice of such a problem. And what I will do is make a quick sketch. Before we do so, copy this to my drawing program. Still the superposition principle example, but I will open up a new blank page and you can have a quick look at this task. So we have a battery and I also have a battery here. Maybe we can also try to have some experiment later on, because there's my document camera and you can see I also have a battery. And I have my lab power supply here. We won't get for sure the very same values because this is a different battery here, but we have a battery, and if the battery is discharged at a certain load, we have a certain terminal voltage of 3 volt and a current of 6 ampere. And if the battery is charged, and I could charge also the battery here with my power supply, and of course I also have resistors to discharge it, then we have at 9 volt voltage, we have -3 ampere that are measured. And so the question is, what is the maximum power that the battery can deliver? And the question is, how would you solve this, or what would you do? When do we have this maximum power output from the battery? Say again? What should be equal to 0? Yeah, the derivative. Okay, that's a pretty good idea. So we could say, okay, the power is current times voltage. And if we draw a schematic for this, okay, we have our ideal source inside the battery. Then we have this inner resistance inside the battery. And then we have the terminals of the battery, and then we have our load resistance or load resistor. So this is the inner resistance, this is the load resistance, this is our internal source voltage. And we could of course say, okay, this current here and this voltage, and excuse me, I'm always bit of confused with the V and the U. Yeah? So if we take the product of these two, then we get the power that is delivered into this load. And so now, of course, we could say, how can we calculate the current in this circuit? Yeah, we take the source voltage and divide by the sum of these two resistors. Inner resistance plus load resistance, right? And how can we calculate the voltage here, the terminal voltage? Yeah, okay, if we have the current, we could say, okay, we take another times the current and multiply the current by the resistance. This would work, okay. So let's take the voltage, once again, the source voltage divided by the inner resistance multiplied with plus the load resistance, and then this is the current once again, and then the current multiplied by the load resistance. So we get something like the source voltage multiplied with the load resistance divided by the total resistance. So this here at the end would also be the same as total voltage multiplied with partial resistance divided by total resistance. This is the same thing as a voltage divider. Yeah, and this would have been my way to calculate the voltage, but you can of course also do it like your way, and of course you get the same result. And so now we see we get already a pretty complicated formula that includes our source voltage and the inner resistance and the load resistance. And of course I can cut one here and like square it. and then we get like voltage, no, this is current squared times resistance, right? At the end we get something like current squared times the resistance, but the current expressed in terms of the source voltage. So this would be our power. And now we would, for example, instead of the resistance directly include the ratio of the resistance and then calculate the derivative of this, set the derivative to 0, because then we get maximum power. And if we do this, what would we find out at the end of this lengthy process? So now take the, let's say, the derivative of this, set this to 0, and the result at the end would be that we get maximum power transfer between the source and the load if the load resistance and the inner resistance are equal. Remember this result? Okay. So the maximum power can be delivered if the load is the same as the inner resistance. So if we have this battery given, what do we need to know from our battery? The inner resistance and the source voltage. This is what we need to know. So what is the inner resistance? What is the source voltage? And how would you do this? How would you solve this? What would be probably some easy way to do it? Try to draw some plot, some kind of schematic that this is our voltage axis and that this is the current axis. And then insert these two operating points. So if we have, so let's say this is 3 volt, 6 volt, 9 volt. And then we have at 9 volt, we have minus 3 ampere. Let's say here is minus 3 ampere of current. So we would get this point here. This would be the discharge. And then at charging, we have a terminal voltage of just 3 volt. No, sorry. This is of course not the discharging, this is the charging. This is the charging. And so when discharging, we have, if then should be here maybe 3 ampere and twice the distance should be 6 ampere. And at 6 ampere, we just get 3 volt. This is the discharging point. And now I could draw a line in between because it's a linear system. Linear systems should behave according to linear functions and linear equations, and the graph of a linear function without this buckle in between, of course, should be a straight line. And from this line or from this plot, from the schematic, now how can we determine the source voltage and the inner resistance? The source voltage should be this junction point here when we have 0 current. This should be our open circuit voltage. And how can we get the inner resistance? Say again? Short circuit. Yeah, so we could calculate the short circuit point here. This should be our short circuit current. That I will maybe call IS. And okay, then we have a short circuit current. How does the short circuit current help us in determining the inner resistance? Yeah, if we just take the ratio between the source voltage that we just got and this short circuit current, then the ratio is the inner resistance. And I mean, at the end, it's the slope here. It's the slope of the curve. It's how much this curve goes down. This is the inner resistance. right? Because if we write a mesh equation for this, we get the result that the voltage here is the source voltage minus the inner resistance times the current. So this is this point. This is the I don't know how to call this intersection here with the y-axis. This is the slope of the linear function, and this is, so it's similar to, I think I'm using gray all the time, yeah, but this is similar to y is n minus m times x, something like this, or plus m times x, and the m is negative, the r is, there's a minus because the curve needs to go down. So from these values, we should need to find this point, and we should need to find the slope of this function. This is at the end what we need to do this. So to find the inner resistance and the source voltage. So looking at what I've drawn here, what would be your lucky guess for the source voltage? Approximately? So here's 3, 6, here's 9. This point could be at, I would say it's at 7. And this point here, this is at 3, this is at 6, could be at 9. So let's say this is at 9, could be 9 ampere. So then the inner resistance is 7 volt divided by 9 ampere. So 7 divided by 9 is something that is not easy to calculate, but it's 0.77 or something like this ohm, right? Okay, so something like this could be also something else here. Could be maybe also 10. Yeah, I would rather say it's approximately something like this. So how could we calculate it more exactly? There's a rule. There's a rule. So we could, yeah, we could have for this inner resistance. Yeah, so for this inner resistance, so this is all approximately. Exactly, we could say it should be the difference from here to here, yeah, between the 2 points that we know, between this point and this point, which is 9 volt minus 3 volt, and then the distance in this direction. Yeah, so maybe I should rather draw to the other side. So we think about some triangle, and we do delta current, delta voltage divided by delta current. Delta voltage divided by delta current, and 9 minus 3 is 6. And here we have 6 minus 3, 6 ampere minus 3 ampere. So this is 6 volt, this is 9 ampere, so we get 2/3 of ohm, and this is at the end 0.66 ohm, not 0.77. Okay, of course, if you know MATLAB, if you know Octave, there are always maybe easier, I don't know, maybe more advanced ways to do this. And so, oops, what I've done now. Here are still the results from our superposition problem that we just solved before. So I will maybe clear everything here. And there's a nice function that is called polyfit, and this will do some kind of polynomial fitting or some kind of linear regression. So we can give this function some values and an order of a degree, and then it will give us back the corresponding coefficients of the polynomial. And so we can try this out. It needs x values, epsilon values, and some degree. So if we check polyfit and our x values, once again, if we take a look at the schematic, the X values are -3 and 6 ampere, right? And the epsilon values or the Y values are 9 volt and 3 volt. And then I'm not sure if we want to have a linear function. What is the degree of the linear function? I would try 1 at first. We will see, okay. And now we get minus 0.66, which is the slope. And the resistance is of course not negative. So our inner resistance would be this as the positive value, and we get the 7 as our intersection here. So the 7 was a very lucky guess. The short circuit current is not a lucky guess, but now I can, as the help suggests, put this into some thing called P. And so the P1 negative would be our inner resistance, and the source voltage would be the P2. And from these two, using this equation here, we could also calculate the short circuit current. The short circuit current should be, how can I calculate short circuit current? If I rearrange this formula, source voltage divided by inner resistance. So source voltage divided by inner resistance, and then we get, okay, this point, as we can see, my schematic I think is not that bad. It's not at 9, it's more at 10.5. So, okay, yeah, maybe I will correct this here and say, go away, my taskbar. This is not 9, this is more 10.5 ampere. Okay, and now this is the thing. This is how we get to this slope, to this schematic. Now, what I suggested to do, and it looks, no, there is it still open. Too many programs open on my computer. There's my LTspice. And on the LTspice, I could now open up a new schematic and try to draw the circuit. So remember, the voltage source could be found here under components, and there is voltage, and I will place the voltage here, and the value of the voltage source was 7. So we give it 7 volt. The value of the inner resistance, so there's a resistor. I know from my experience that positive current is counting downwards. If I rotate it with Control R, as suggested here in the lower left corner, now current will flow to the right, to the top, and to the left. So this should be my, I will rename this to inner resistor. What was the value of this? Yeah, it was. Yeah, the current is 10.5. The resistor was 2/3 ohm. So I can insert something like 2/3, but to make it a valid statement here in LTspice, I have to put it in curly brackets. So then it will work. And then I can place some load resistor here that I will call RL. I will use a capital L because the lowercase l is always difficult to distinguish from an I and so on. So now we can put everything together and place a ground node. Remember, we always needed to have this ground node. And I can label with this function here. And so now what happens in the background, check the lower left corner if you see it. What LTspice does in the background, it automatically numbers these nodes. So this is node N001. This is the node N002. And I want to give this a distinct name. So I take the label here and label this as V load, the voltage at the load. Put this here, connect this, and now it says, okay, this is node VL. Now I've given this node a name for my load voltage. Okay, So we have a nice circuit. We have just redrawn the circuit that I've here also sketched. And now we would like to see this curve. And the curve, and as my tablet is really dying now, where's my back? I would like to connect a charger. Here it is. So maybe I can. I thought that it will do it, but it won't. Okay, this looks good. So now we want to see the same schematic here. So we need to, what do we need to do to get this? To see the same curve here, the same behavior also in the LTspice simulation. Yeah, of course we need to do some DC operating point solution. But, okay, yeah, so as the task says, if we have a 0.0 ohm load, we should get a terminal voltage of 3 volt and a current of 6 ampere. So if I set the load to 0.5 ohm and try it out, simulate, do some DC operating point solution, then we get a result, and the result says, okay, yeah, we now get at our node here, we get 3 volts as voltage, and through both resistors, we get 6 ampere of current, and through the source, we also get, of course, 6 ampere of current, but it's counted negative because, yeah, in LTspice, I don't know for which reason, current would also flow. Positive current would flow from plus to minus, but our current is flowing in this direction, not in this direction. And that's why the current that we get here from the simulation result is negative through the source. Okay, so maybe somewhere makes sense, maybe not, I don't know. So now we get just one point, but we would like to see this curve here. So how do we get the curve? What would we need to change? To get to different points on this curve. And so if I take red and say, okay, this 0.5 ohm load, so voltage is resistance, load resistance times current. If we draw this, voltage is resistance times current into our schematic that we have here at the bottom. How would a curve like this look like? It's the same as y is m times x. The characteristic of a resistor in a voltage current diagram according to Ohm's law, it's just a straight line going up. Yeah, with a slope that corresponds to the load resistance. And the point where the load resistance curve and our source curve hit each other, this is the operating point of our circuit. This is the operating point that we just found here by doing where's the simulation control panel, edit simulation command. That's why it's called DC operating point solution, because we find the DC operating point of the circuit. Yeah, an operating point means where these two curves intersect. So now we want to, if we do not only want to see this point, but if we want to see the whole curve, what should we possibly need to do?
Equation of the curve?
Yeah. We need to change the resistance. We should need to go to higher resistors with higher slope to the red curve, and we need to go to lower resistors with smaller, and then we get an intersection here, an intersection there, an intersection here, an intersection there, and all these intersections, and then we should get a curve. We should get the same curve that we've seen before. Okay, so we need to have many of these resistors. We need to step the resistor. So let's check the help, because I also always forget how it's done. And there's some step operator or some step command that does parameter sweeps. And you can see we can do something like step, and then we can step some load resistor according to a list, for example. So we want to, this is what I will copy, and then edit and insert some, where does it work here? Some spice directive, and insert this. So we want, our load resistor is called like this, RL, and I would just say OK and place it somewhere here, and then with space on the keyboard go back. And so I think now if I click on this with the other mouse button, then some magic menu opens up where I can say, OK, I want to sweep this load resistor RL, and I don't want to do a list, I want to do a decadic sweep, some logarithmic sweep. And I want to go from very small values, maybe a milli ohm, to some very large values, maybe 1 mega ohm. From milli to meg, and per decade, I don't know, 10 points should be enough. I mean, at the end, it should be a curve. And so from 1 milli to 1 mega ohm, it's 6 orders of magnitude, 6 decades. So with 10 values per decade, I should get something like 60 simulations, or maybe 61. So if we run, if you check the load, so now it starts some analysis, takes some time, interestingly. Hopefully my computer does not crash, because it should not be too complicated for it to do such a sweep. Okay, it doesn't. It did 91 runs, of course. From 1 milli to 1 meg, it's 9 orders of magnitude. Yeah, and that's why. Okay, we get 91 runs, and it says it's just, maybe my computer is really slow at the moment. Or maybe I should reduce the number of runs. Usually this should be done within seconds and not within minutes. But it's doing these runs, and maybe I will just wait. Maybe I should omit the plotting at the same time. Maybe then it's going faster or not. So in the lower left corner, you can add, as you can see, this should be the usual speed. That it's really going through all these simulations very rapidly and quickly. I don't know what my computer is doing in the background. Okay, so there's a schematic. Which is empty yet. I will try to make them fit on the window at the very same time. And so what we've displayed here is the voltage. So I will also plot the voltage. There's this nice voltage probe that helps me to plot the voltage. And then we can see, okay, something is happening here. I don't really see a line at the moment. Okay, the line is steady at 3 volts. Okay, maybe my simulation is rubbish because it still uses the 0.5 value. So I maybe need to switch this to RL and rerun the simulation once again and close this so that the simulation runs a bit faster, but now it should already be finished. And we can tile the windows once again horizontally. Okay, so there's now a curve, the voltage at the terminal, but as a function of the resistance. I want to have the voltage as a function of current. So I need to click on this line here, maybe with the other mouse button, and say the plotted quantity should be the current through the load resistor. Hey, and there's our curve. Okay, and the good thing is we see the very same curve. The bad thing is it's not that nice yet because we don't get to this side. So how do we get to this side?
Even negative value?
Yeah, but we cannot, I think we cannot give the resistor negative values because there's no negative resistance in real life and not even in the simulation.
Can we flip the source?
Yeah, we could somehow flip the source, but the problem is that at this, if we are moving from this first quadrant to the second one, our battery, in this case, here it's always discharging, here it's charging. And by just having a resistor on this side, we will never ever get it charging. So yeah, we need to add a source. So I will maybe, if I can, try to copy all this stuff here and then open up a new schematic and paste it there and take the delete button on my keyboard, delete this resistor, insert another source, a voltage source that would charge and discharge our battery. And I will, I don't know now, I will call this VLoad. Or maybe, I don't know, maybe this is confusing it because maybe I will call it VCharge. And I will also give it the value VCharge. And now our step command here should not step RL, but the VCharge. And now we can do a linear sweep. We can start at 0 volt and go up to 9 volt in increments of 0.1, for example. Then we should also get 90 sweeps. And run. And then it's doing something and it's completed 90 runs. And now once again we can plot the voltage here. And the voltage here, of course, it's the voltage across the source. The voltage is going up, but it's the voltage, I think, with respect to the voltage. Does not make too much sense. On this axis, what we would like to have there? The current, exactly. So we change this to the current that goes via the inner resistor. And now, I don't know for which reason this is now RI1. I think because I copied it. And then we get this curve. Of course, the curves look pretty similar, but here we now have, this would be our y-axis, or this would be the voltage axis, and now we go to the negative side and we have this 9 volt, minus 3 ampere, 0 volt. Yeah, I can also put a marker on here. The marker window is unfortunately always hidden behind my camera window. So and we can move the marker up and down with the arrow keys on the keyboard. So we start with 9 volt minus 3 ampere. Here at the 0 we have, yeah, not exactly 0, but minus something milliampere, 0 volt. And then we go up to 10.5 ampere and 0 volt of voltage. Okay, this somehow nicely fits. And as a nice solution of this task number 19 here.